right. Yeah, good afternoon, everyone. I'm Pedro. I'm a software engineer here at Meta. I work with compute engines in the data infrastructure team. And I'm here to talk a little bit more about our experience supporting machine learning users in Presto and kind of in compute engines in general. So I think first of all, like I attended PrestoCon a couple of times, but it's my first time as a speaker. So really excited to be here, and thanks everyone for having me. All right, so just as a quick background, I think like everyone knows, machine learning is today becoming the largest consumer of data management. And this means not only that most tables and most data is today kind of targeted to machine learning workloads and training and things like that, but also that a lot of compute goes into kind of training those models and kind of preparing data so that those models can be trained. And I think at this point, there's no reason to believe that this trend will change anytime soon, right? So if anything, like this will grow even larger. Like we see a lot of the use cases kind of transitioning from kind of more traditional analytics into machine learning. So I think like this trend will probably go continue increasing, and more workloads and kind of data and models we will move into kind of machine learning sort of infrastructure, right? At Meta, people usually love Presto. Like, we have a nice SQL dialect. It's pretty convenient. It's easy to use. It's kind of fairly well integrated with everything. But somehow we still see that machine learning is not really a big user of Presto for some reason, right? So we see that there's a lot of use cases where people could actually still use Presto to create the training tables and things like that, but you see that people don't use Presto as often, right? I think one of the big questions I try to answer, and I try to summarize on this talk is why. Like, what are the reasons? What are the things kind of missing or optimizations we can add to Presto to better serve this class of use cases? So just as a quick context, I'm not a machine learning expert here, but just kind of on a very, very high level. In machine learning, you have those little programs called models, and models can usually make predictions, right? So then for you as a user, we specify features to models, and features you can imagine as essentially like parameters, right? So for you as a user, you have your demographic information, you have some other information you pass to your model, and then inside the model, you can go through the inference process and then kind of generate predictions, right? And then this could be from kind of ranking things for recommendations, things like, what is the next ad or next piece of content we should recommend to this user, or we should show to this user. So whenever models make recommendations, we log those predictions. So imagine that a user, or we generated a recommendation to a user. We will log this data along with all the features that we use to make this prediction, and those things eventually they make their way into the warehouse or into the lake house. And there's a series of kind of ETL processes that kind of massage this data and kind of aggregate them and join in with some other resources. You can imagine that for things like when you make predictions, there's also kind of, you usually log what was the prediction from the model, but there's also like what actually happened in practice. So for example, if you suggested an ad for a user, that the user actually clicked on this or not, and usually this data may come a little later or in some sort of async fashion. So there's some process of kind of curating and then massaging this data until in the end of the day you generate a training table. And this training table is kind of used to train new models, and then those models are deployed to production, right? So there's this cycle of making predictions on the website or in production, logging what are the predictions, and then using this to kind of improve your model, right? And then, of course, like the more data you have, the more examples, the better your model can be, the better your model behaves. So like I said, on the lakehouse, there's this process of training data preparation, which is essentially kind of curating this data. A lot of that actually runs in just traditional compute engines. So a lot of this runs in Presto, runs in Spark, while the actual training process and making inference on models are things that run in libraries like PyTorch. So this talk focuses a little more on this problem of training data preparation, right? Or just to kind of situate where this thing sits into this whole ML flow. The interesting part is if you look at what people do into those workflows while preparing training data, there's nothing very different from just traditional SQL kind of relational operators, right? So people join tables, they filter, they apply expressions, sometimes they do aggregation. So there's nothing very, very different from that. Yet it's very common that people, they just don't use compute engines, right? They come up with their own thing. And this is what we have observed. Like I said before, people usually they love Presto, so they try to use Presto. In many cases, Presto doesn't really work. Sometimes it just runs out of memory, or your query takes too long and then fails, or a query fails right away. In many cases, people try to use this new version, this version of Presto that runs on top of Spark and gives you a little more scalability. Sometimes it works, but in many cases it also doesn't work. But then, as kind of sort of a last resort, they can try to rewrite the query in Spark SQL and then just run as a kind of a native Spark pipeline. But we also saw that in some cases, not even running Spark SQL really works for them. So it's really common that ML users and kind of product groups supporting machine learning infrastructure, they end up creating their own engine. So it's really common that people actually create their C++ binaries. They use libraries that can parse Parquet files, and then they actually code the data manipulation instead of using engines, which are things that have been developed for 10 years to do that. Right? So I think the focus of this talk is, again, like how can we, what's missing in our engines, and how can we be more efficient about those use cases. Kind of digging into why are those things more efficient and which parts, and why they can be smarter than us in some cases. But essentially trying to see what we can learn from those use cases and what are the things that we can bring to our engines. And of course, in the end of the day, like we want to kind of minimize how many custom solutions people have to build and just kind of make them move to a more general purpose engine like Presto. So if you summarize this talk, like there are three main things that we learned in the last few months of actually engaging with machine learning users. So I'm trying to kind of summarize or organize the talk in those three main areas. There's a few things related to the storage layout of the data. There's a few things that can be more efficient regarding the in-memory kind of the in-memory layout of this data, like how we represent this in memory. And there are a few things that can be added or can be improved, and essentially how we execute and how we process our relational operators on top of this data. So starting with the storage layout. So just with a quick background, like I said, features are those kind of parameters that we use as input to models. As you can imagine, like the more features you have, usually the better predictions you can make. So it's really common that in some cases those tables, they have a very large number of features. Like, so it's really common to see thousands to tens of thousands, or maybe even hundreds of thousands of features inside the same tables. Not just you have many features, but those features are commonly getting added and removed. So they usually not model as actual columns on those tables, but rather they are modeled inside maps, right? Just because then you have a lot more flexibility in kind of adding things, and you don't need to change the schema. Also, for historical reasons, this is just what happens, not just at Meta, but in many companies in the industry. Feature data is essentially represented as maps. Those features can be many things. In many cases, they're just integers. They can be floats, but they can also be arrays of numbers, and they can also be maps of things. Right? So in the end of the day, the schema is really common that you have your features. They always map a feature ID to feature value. So in many cases, a map from an integer to an integer. In some cases, a map from an integer to a float, or from an integer to an array of other things. Right? So you can see that the schema of those things start getting kind of nested and more complicated. Right? Even kind of more complicated than that, is really common that the features themselves can be sequences, right? So I think one of the things that machine learning people have found through years of training models and improving the accuracy of those things is that, for example, to make recommendations, like it's really useful if you see the list of things or kind of list of ads or list of contents that the user has seen in the past. And this means that it's actually a feature to the model. So in many cases, you have those, one single feature for one single row is actually a very large list of elements. And as you can imagine, the longer, the better. So in some cases, like we actually want to look at many days or many weeks or, many months of history of how, what's the kind of history of the of pieces of content or elements that the user have interacted in the past, and then we use this as a feature in the model because that improves the model accuracy, right? So this is, improves the model accuracy, but you can imagine that this creates sort of the generate tables that in some cases are very, very wide. So sometimes those columns can be very, very large. We have some cases where columns themselves can have more than a megabyte, like a single, value for a single row. So you can imagine that, tables as we understand them, usually they're really tall, right? So you have a few columns, maybe hundreds of columns and billions of rows. In this case, you still have billions of rows, but the columns are much, much wider, right? So the scale over all of those things is not just the scale is larger, but they actually, they're kind of scaled in a different way as kind of traditional tables. Just another piece of background, like of course, as we model those things as map, hope this is not news for many people, especially those who actually work on the P engine. But usually the way those things are represented on the storage is everything is stored column-wise. Specifically, when you have things like arrays and maps, those are usually stored contiguously on a region of disk. So all kind of keys and values of a map or the elements of an array, they're kind of stored contiguously on one stream on disk. Right? Of course, if you have a map, you usually have one stream for keys, one for values. You also have one stream for sizes of things, but this is sort of how those things get mapped, right? So if you look at one contiguous region on disk, you usually have all the kind of different keys and values and elements for one particular row. So this is pretty good, but one of the things that people do very often is this thing called feature projection, right? So when you have your training table, you have many features. Usually when you're training your model or when you do any type of processing, like it's common that people just want to pick a few features, right? So when you have this sort of logical layout, it's not very convenient to do so, right? So imagine that if you have this, if you want to just read feature one, it's the data is all scattered on disk, right? So this cannot be done very efficiently. So one of the things that we created over time is this thing called flat maps, which is essentially like, well, it's still a map logically for the user, but we sort of store this on disk as a struct, right? So essentially we group all the kind of features or the keys or the values that have the same keys, we group them together. Of course, this makes it more convenient for feature projection because then you can just go and read one region, but it also creates smaller streams, right? So in many cases, this doesn't compress or doesn't encode as well as it would before because you had kind of fewer but much larger streams. So in this case, if you want to do feature projection, at least we go usually with a single IO, or at least like with fewer IOs, you can execute the thing. So first thing we need to do is just making sure that those things are kind of properly kind of laid out on disk. Second thing that comes with this is that because now you create one stream per distinct value for a feature, this might end up creating too many streams, right? So if we start with the assumption that you can have more than 10,000 features, you end up having more than 10,000 streams, right? So another thing we've seen over time is that doing those things over traditional file formats like ORC or Parquet, they're not very efficient because they were never optimized for this use case of having like very wide tables with way too many features, right? So we saw that in many cases, first the metadata is kind of scattered through all the file formats, so you end up having many IOs to kind of reconstruct the file structure, but also just things like parsing and understanding the protobuf and thrift metadata, like it just really adds up, and this is kind of the main thing and the training process. So the first takeaway here is that just kind of reusing traditional file formats doesn't really cut anymore. So we need to somehow organize the data better, focusing on parsing or having something that allows us to parse the metadata a little faster, but also kind of really optimizes for this feature projection use case. Another part is feature encoding. So you can imagine that we store many features, and those things are usually denormalized, right? So if you have records for the same user, usually the value of at least many of those features, they actually have a functional dependency on user, right? So there's a lot of kind of repetition on those things, and this gives us opportunities to encode this data much better. Problem is if you use traditional file formats like Parquet and ORC, they kind of limit how you can encode kind of nested and especially deeply nested values, right? So you usually cannot have like a struct with arrays with things that are kind of dictionary encoded and bit packed and things like that. So we also need a better file format that allows us to, in a way, kind of cascade those different encodings. Especially if we're talking about those long sequences, right? Because those are kind of really long arrays that if we can actually deduplicate them across rows, we really want to do that because that's a big storage saving. Again, we need a more kind of optimized or a better file format that can allow us to be more flexible, hopefully allowing us to kind of cascade different encodings, but also that at least allows us to also kind of decouple the encodings from the file format. Another thing we have observed is that the kind of the encoding or the different techniques you have to encode data, they usually advance a lot faster than the layout itself. So we also want to kind of decouple those things so that we can have the same kind of file format with the same layout, but maybe with time kind of easily adapt the encodings and extend them without having to kind of make backwards incompatible changes to the file format. So the first takeaway from the talk is just, well, to better support feature projection, we need a better and new file format. So first, we need an efficient way to represent maps, because this is where features are stored, and this is essentially where most of the storage goes. We need better support for those really wide tables that have many features, and we need something that a file format that's more flexible and allow us to extend encodings without changing the format itself. So I'm not going to give too many details, so that's why we created this new file format called Nimble. We used to call it Alpha. It was recently open source, I think a few months ago at this point. We have a talk later today by Jiliang and Jimmy, and they're going to dive into a little more details. Right? But essentially, this is why we ended up creating this format. It's initially, right? It's something that can be more efficient for machine learning workloads, kind of specifically for training, and allows us to be more efficient while we kind of do feature projection. So this was the first part of the talk. And the second one, I'm going to dive a little bit more in things that we can improve regarding not just how data is laid out in storage, but how data is laid out in memory. So as a quick example, we have this thing that we execute commonly for ML workloads called feature injection. This, you can imagine that you have your samples that are coming from logs. And you also have some features that are computed offline through different processes. And in the end of the day, we actually want to kind of combine offline features on your training or with your training samples and generate a training table. So essentially, you're joining two tables and you're combining keys from different maps, and you're creating the output training table. And like I mentioned, like this process of kind of joining, but executing all those operations, this is what we call training data preparation. So yeah, so now we're in a world where we have flat maps, so at least the storage layout of those things can be efficiently. But another thing that people do very often is just moving this data around, right? So assuming that you're reading from a table that actually has features represented as flat maps, what happened when you execute a select star from that table and, for example, ingest this data onto another table? So the first thing you do is, well, we don't have a native way to represent flat maps. So the first thing you do is you're going to actually convert this flat map storage layout into a map in memory. And this in itself can be a very costly conversion, assuming that, well, those columns are large and then you're reading a lot of data. So another thing we observed in many cases is that if you actually profile some of those large queries, they spend a larger percentage of time on just this conversion, right? Kind of reading flat maps, which have a nice layout, converting them into maps, because that's the only memory representation that the engine can understand. So I think we've been discussing one of the things we're planning to work on is where we actually need to have a kind of corresponding flat map in memory representation. You can imagine there's a sort of a different encoding for maps. So a map could then be just, well, represented as using the kind of the regular map layout where you have two streams, one for keys, one for values, but maybe can have an alternative encoding. And this, of course, adds lots of complexity of, like, if you look inside velox, for example, like if you have UDFs and all the different operators that expect maps, they can get different encoding on those maps. So we need to actually handle those different use cases. But this is something that can buy us a lot of performance. And again, if you, as a machine learning user, if you execute a query, you spend 50% of time kind of just shuffling things around, you can easily come up with something more efficient, and then you end up not using the engine. Right? The other thing is kind of minimizing read-write conversions. So I think another thing we've been seeing is that now that the storage layouts with Nimble can be more efficient in coding and cascading. We need to, as much as we can, as we read this data from disk and represent them in memory, we want to try to keep this encoding as much as we can, right? And kind of the same thing as on the other side. So essentially, the storage data API needs to be wider, right? So for example, if you're reading a dictionary, we should preserve that as a dictionary. Right? If you're reading something that is a struct of arrays of dictionaries of something else, we need to, as much as we can, preserve this in memory and give this to the engine so that the engine can figure out what's the best way to process the data, rather than just kind of flattening everything. And another thing we've been seeing in some cases is that same thing on the writer. So in some cases, the engine, as you process your operators, you actually generate data that's encoded. But in many cases, the table writer doesn't know how to handle that. So you end up having dictionaries and you flatten, you pass this to the table writer, and then you have to kind of dictionary encoding things again. So there's a lot of opportunities there, and we've seen kind of the same thing. In some of the use cases, we do spend a lot of CPU just doing these conversions because the storage layout and the in-memory layout, they're not as compatible. In some cases, they are compatible, but the API allows you or kind of force you to flatten and encode the data again. So the second takeaway is that just as much as possible, we want to, we want to be efficient as how we represent those features in memory, but we also want to avoid conversions between the storage and in memory layout. Just quickly, I know that we're running out of time, but just kind of the quick last topic about execution. So another thing we've been seeing is that in many of those cases, because the values for some of those columns can be really large, tables become very, very, very wide, right? And this means that if your columns are too wide, you need to try to copy data as few times as you can, right? So I think we came from the assumption that kind of copying rows is just copying integers and is not as much of a big deal. In those cases, you actually want to prevent copying rows during execution as much as we can, right? So we have this thing called compressed execution, where the idea is essentially to avoid copies as much as we can by leveraging encodings. And this is kind of go both ways. One, leveraging the encodings of the input data to do things like if you're executing expressions, you can only execute expressions over the distinct values of maps, but also things like in some cases, you can actually execute operations more efficiently by just kind of wrapping dictionaries and wrapping encodings around the data. Just quick examples of this, what this means. Usually on a regular execution, for example, if you're joining two batches from two table scans, you usually execute the join operation, and you copy the value of all the columns being projected. While in a compressed execution engine, you can just kind of wrap those things around dictionaries and kind of reuse this data, right? And then in the end of the day, you avoid this copying, which can be a lot more costly in those use cases. And then the last thing is just kind of leveraging lazy evaluation as much as we can. So I think if we're getting to a mode where the engine does compressed execution and allow you to execute a lot of those operations by just playing with the encoding, in many cases you actually don't need to know what's inside the column, right? So if you want to filter out something, you don't need to necessarily know what's inside, right? You can just wrap this data around a dictionary that, for example, skips some of the data. Right? I think there's this idea of kind of lazily reading those values, because I think the further you end up evaluating those things, the better, because you might need to read fewer things from disk. But then there's also this idea of moving forward. If you actually need to materialize those things only on the table writer or on the kind of consumer or on the producer side of a shuffle, I mean, in many cases, you might be able to kind of skip decoding the data whatsoever, right? But just kind of taking a blob of data from the table scan and delivering this blob of data to the table writer. Here, there's a lot more questions than we have answers. Like this is something we just started investigating. Happy to collaborate with any of this if people have ideas on how this can be leveraged and how we can make this more general. But I think the observation is that, again, in many cases, because we don't do that, people end up creating those bespoke small compute engines that actually do that by design, and then they can be a lot more efficient. Just as a last quick takeaway, when executing queries, we should, as much as we can, leverage compressed execution tricks, so we minimize the amount of times we need to copy those really large rows. But we also need to focus on kind of materializing things as late on the query plan as we can, because in many cases we can skip the reading, and if we can skip the reading, at least we can skip decoding this data. And again, because those things are large, this thing can really add up. So just to quickly wrap up, machine learning is becoming the single larger consumer of data management today. So we kind of identified and we proposed a series of improvements to storage layout and memory layout and execution that can help us serve better this class of workloads. And I think, of course, the idea is reducing the need for kind of specialized and bespoke solutions, and just hopefully getting more and more machine learning users to use Presto. Happy to answer any questions, and that was everything I had. Thank you.